Hi everyone, I'm Qianyu, graduated with a Bachelor of Computing and Math from Queen's University. Now I'm working as a software developer at an investment banking. Prof. Muise is my supervisor at school and also made a great contribution to this paper. He's experienced in AI planning and he's really patient to teach his students. I'm sincerely thankful to Prof. Muise. The title of paper is Action Usability via Deadend Detection. The initial idea comes from a common issue when I develop planning problems in PDDL. My model failed sometimes, and I didn't know why it failed. Contrasting with other programming languages, PDDL modeling tools rarely have their own syntax checking and analysis to aid in the modeling. It's quite time-consuming for modelers to debug this error without any system debugging tool to tell us why the error occurs, or which part of the script might be causing the error. There are a variety of possible planning-specific analysis, and we present one such analysis, detecting unusable actions. Unusable action is a terminology describing an action that can never be executed in the model. We use action usability detection for the on-the-fly diagnosis of planning models. We achieve this through the repeated reformulation of the original model. The key insight is that we can introduce a special fluent F0 that action achieves, and replace the original goal with F0. Doing so provides us with a new model that has a solution if and only if the action is usable. The goal can be achieved only if the action can be executed. Before digging into the reformulation of the problem to detect the unusable action, let's see some background knowledge. First, the deadend. We mentioned it in our title by deadend detection. Deadend is also called unusability. In automated planning field, it is the task of determining if the goal can be reached from a given state. It indicates that there's no solution to the problem, which means not all goals are achievable. In our paper, we talk about the problems that we reformulated based on the action usability algorithm. If the reformulated problem is deadend, then we see the modified action is unusable. Then action usability. This is the question of whether or not any state can be reached by a sequence of executable actions. PDDL editor. It helps the creation of planning tasks written in PDDL. Our work is exposed as a customized plugin on the online PDDL editor. We refer to the problem reformulation process as the action usability algorithm shown in this figure. This is a crucial part of the paper. Let me explain this algorithm clearly. Each action is evaluated in turn. We take one action, A, belonging to capital A, as an example to explain the details of the evaluation. To set the execution of A as a temporary goal, we assign a new fluent F0. Here, the F0 to the effect of action A, the effect of action A, and as well as the goal of the planning problem. To guarantee the new goal is satisfied if and only if the testing action is executed, the new value F0 has to be different from any existing state. Otherwise, it is possible that the goal is achieved because of alternative action. Since F0 doesn't exist in the original domain, it is important to append it to the set of predicate F' before using F0. Then, it calls a sound and complete planner to find the plan for the modified problem. If a valid plan is returned, A is considered as a usable action. If not, then A is unusable. We want to test only one action each time to make sure that each action has its independent testing result. Therefore, before checking the next action, the effect of the current action needs to be reverted back to its original value. Let's move on to the implementation. We have implemented this approach and exposed it as a service integrated with the online PDDL editor, which is created by Prof. Muise in 2016. Users of the online editor can directly analyze their PDDL models, and the problematic actions will be indicated directly in the editor itself. I'm going to use this link that already has the plugin and a common logistic domain example to demonstrate our plugin. In this problem, there are two cities. Each city has a post office and an airport. There are 6 objects. 3 objects are located in post office. The other 3 are in post office 2. Our goal is to move the object 1, 2 to airport 2, and object 1, 3 to airport 1, and so on. The difference between the working domain and the broken domain is the precondition of the load airplane. Let's see. So here, the load airplane, right here. It switches the position of the object parameter with the location parameter. And here is the incorrect one. Let's just run it. Typically, we just click the analyze if we want to run the working domain. I have already run this, so let's just see the results. And this is the result. All actions are usable. And if we use the broken domain to analyze, here is the broken domain result. The load airplane and unload airplane are unusable. The problem action is correctly identified, but note also that the unload airplane action is also identified as unusable. This makes intuitive sense, as you are only able to unload an airplane if there's something already loaded. Since the initial state doesn't begin with any package loaded, then the unload action becomes unusable as well. Lastly, in this paper, we represented a simple yet powerful model debugging technique for detecting when actions are unusable, and additionally provided an integrated solution into model modeling tools. Down the road, it would be interesting to perform a deeper analysis of the unusable actions to detect which ones are the root cause of unusability. For instance, in the load airplane example, the unusability of unload airplane is caused by the incorrect prediction of load airplane action. Suggesting such target analysis is beyond the scope of this work, but it's an interesting path for future work. Thank you so much for your listening.